Okay, so I think we are going to see quite a, let's call it a beautiful proof. The only problem with that, I'm going to give the motivation more than precise answer onto how to prove what is the Jordan form for a block of Jordan to the power of n for this kind of block, as you see right over here for a Jordan block like this. Now, this is a beautiful proof because you'll see that it combines some very simple and quite beautiful techniques. I'll just separate the Jordan block to two matrices, which is very simple matrices. One is lambda I and one is the nilpotent n. And then, very beautifully, we'll use for it the binomial theorem, as you can see here. What a connection. And then you will see how it goes, and then we will get a very beautiful, just simple and beautiful answer to what is the Jordan block to the power of n. As you can see here, the eigenvalue to the power of n, and then n1, n on 1, eigenvalue to the power of n minus 1, and the other, call it super diagonal, n to the power to 2, and here is n minus 2, lambda. So you can see the pattern here. Beautiful pattern, beautiful way of proving, and beautiful idea. So let's start. So we start with a Jordan block and we ask ourselves how the j to the power of n looks like for a block of the eigenvalue lambda. The block is of size m on m. This is the block, Jordan, eigenvalue on the diagonal and the super diagonal ones, and everything else is zero, like a Jordan block. Now we can separate this matrix, this Jordan block, to lambda I plus n. Lambda I is the identity matrix multiplied by lambda. So this matrix is just lambda on the diagonal and everywhere else 0. And n, which is a nilpotent matrix, which is just the part of the ones on the super diagonal, the first super diagonal. So this is n. Now there is a, let's call it a lemma or whatever you call it, that says that for a nilpotent matrix like this, in size m on n, it's nilpotent to the power of m, namely n to the power of m equals 0. And n to the power of m minus 1 is not 0. What happens is, let's see what happens because it's important. If I take this n and raise it to the power of 1, so nothing changed, but if I raise it to the power of 2, all the ones just go to the next super diagonal right over here. First on the second super diagonal, ones on the second super diagonal. If I take the n to the power of 3, again, the ones go one step further to the next super diagonal. So ones going from here to here, n to the power of 4. You can see another step on the super diagonal to the fourth super diagonal, and etc., until we get to the n to the power of m minus 1, which is 1 over here, n to the power of m. Everything is 0. So this is, of course, not a proof. This gives you a motivation as to why I say that n to the power of m, which is the size of the matrix m on m, is 0, and n to the power of m minus 1 is not 0, it's just 1 over here. Okay, so we said that the Jordan block can be separated into the sum of those two matrices, and now we want to take to the power of n because we want to know Jordan to the power of n, block Jordan to the power of n, what is it? So we take this separation and raise to the power of n, and here comes the binomial theorem very beautifully. You just sneak in as we didn't think about it. So we have the binomial theorem. Do you remember it? The sum from j equals a 0 to n, which is the power, n on j, times lambda I to the power of n minus j, times n times to the power of j. Now, we don't really need to go until n, assume n is greater than m, because you know that for every m or above, n is 0, n to the power of m is 0, and here we'll get 0. So we just need to go until m minus 1. Everything else far beyond it will be just zeros. So we'll go until m minus 1. So again, this is the binomial. Again, the same idea. Now, this is just the identity matrix. You can just take it off, okay? So we don't need the identity here because it's just like 1. okay? Because I times the matrix is just a matrix. Okay, so define it as we saw. N to the power of s is just 1 on where I said. We saw it here, so you know it. You know the idea. So what we get? We get that if you look right over here, think about it. If you think about j, to which j should we look at? Now, we should we can look on n to the power of 0, and remember that every matrix to the power of 0 is just the identity matrix. So if we look on n to the power of 0, it just times lambda power n minus 0, so lambda n, times n above 0, which is 1. And this is n to the power of 0 is just 1 on the diagonal. So I will get lambda times 0 times 1 times the identity matrix. So we'll get just lambda to the power of n on the diagonal. Now let's move on. N to the power of 1, j is 1. Lambda to the power of n minus 1. N to the power of 1. And n to the power of 1 is 1's on the first super diagonal. Multiplied by lambda to the power of n minus 1, n minus 1, n minus 1, n times n above 1, n above 1. Let's move on. N above 2 times lambda n minus 2 times n to the power of 2, and we saw that we need to continue to the next one. Here we just did a very simple m equals 3 matrix. So n to the power of 2 is here. It's just 1 over here. Everything else is 0. So we get 1 over here times n minus 3 lambda to the power of n minus 2. Lambda to the power of n minus 2 is here, and n above 2. And we do summation of all of this, and we get lambda to the power of n here, what we said here, and what we said here. You can see the pattern, and this is the general form for a matrix of size 3. You can conclude it for every size of a matrix. Of course, if we had a matrix of 4, so we'll have here this one and another one, and here it will be lambda to the power of n minus 3 multiplied by n above 3, and etc., etc. But you see the pattern continues. Quite beautiful. And this is it. This is the Jordan block to the power of n, the general idea. Depends on your eigenvalue, of course, and the power n. But this is quite a beautiful result for a Jordan block to the power of n. From here, with the nilpotent matrix, we just split the Jordan, got the sum of two matrices. On this, to the power of n, take the binomial. From the binomial, we could conclude how the Jordan block to the power of n looks like in the general form. Quite beautiful. Nice, right? So I know that I was not very, very accurate, but I wish that I gave the motivation for this. We also understood nilpotent matrix with one on the super diagonal, how it looks with its powers, the one just go ahead with the power. I wish it was quite understandable. Thank you very much. If there are any mistakes or corrections, please tell me. But anyway, thank you very much. And this is about Jordan block to the power of n, and that's it.